Magnetic Fields Chapter 26 Definition of B. 26.2 The force exerted by a magnetic field. Definition of B. 26.3 Motion of a charged particle in a magnetic field. Applications: a circulating charged particle, crossed fields, discovery of the electron, the cyclotron and mass spectrometer. 26.4 Magnetic force on a current-carrying wire. Last lecture. This lecture. Magnetic force and field. The definition of B. The sign of Q matters. Find expression for radius, r. Charged particle moving in a plane perpendicular to a uniform magnetic field, into page. Find expression for radius, r. Checkpoint. Here are three situations in which a charged particle with velocity v travels through a uniform magnetic field B. In each situation, what is the direction of the magnetic force Fb on the particle? Left. Up. Into page. Right. Down. Out of page. Answers: A, plus Z, out. B, X, left, negative particle. C, 0, checkpoint. The figure shows the circular paths of two particles that travel at the same speed in a uniform B, here directed into the page. One particle is a proton, the other is an electron. Which particle follows the smaller circle? A, P. B, E. Does that particle travel clockwise or anti-clockwise? P. E. Answers: A, electron, smaller mass. B, clockwise. V equals EB, velocity selector. Crossed magnetic and electric fields. Net force. The force is balanced if the speed of the particle is related to the field strengths by QVB equals K. V equals EB, velocity selector. Measurement of QM for electron. J. J. Thomson, 1897. Exercise: find an expression for QM. Sun to Aurora TV analogy. A small part of the sky overhead. Checkpoint. The figure shows four directions for the velocity vector v of a positively charged particle moving through a uniform E, out of page, and uniform B. Rank directions A1, B2 and C3 according to the magnitude of the net force on the particle, greatest first. Of all four directions, which might result in a net force of 0. A1, B2, C3 or D4? Answers: A, 2 is largest, then 1 and 3 equal, Vxb equals 0. B, 4 could be 0 as Phi and Fb oppose. Velocity vector is in the y direction. Example: the magnetic field of the Earth has magnitude 0.6 by 10 to 40 and is directed downward and northward, making an angle of 70 degrees with the horizontal. A proton is moving horizontally in the northward direction with speed v equals 107 meters per second. Calculate the magnetic force on the proton by expressing v and b in terms of components and unit vectors, with x direction east, y direction north and z direction upwards. Picture the problem. Velocity vector is in the y direction. B is in the yz plane. Force on proton must be towards west, E in negative x direction. Circular motion of a charged particle in a magnetic field. The cyclotron. It was invented in 1934 to accelerate particles, such as protons and deuterons, to high kinetic energies. S is source of charged particles at center. Potential difference across the gap between the Ds alternates with the cyclotron frequency of the particle, which is independent of the radius of the circle. Schematic drawing of a cyclotron in cross-section. Schematic drawing of a cyclotron in cross-section. Ds are housed in a vacuum chamber, important so there is no scattering from collisions with air molecules to lose energy. Ds are in uniform magnetic field provided by electromagnet. Potential difference V maintained in the gap between the Ds, alternating in time with period T, the cyclotron period of the particle. Particle gains kinetic energy QV across gap each time it crosses. V creates electric field in the gap, but no electric field within the Ds, because the metal Ds act as shields. Key point: Fosk equals F equals QB/2 m is independent of radius and velocity of particle, the cyclotron. Example: a cyclotron for accelerating protons has a magnetic field of 1.5 t and a maximum radius of half a meter. What is the cyclotron frequency? What is the kinetic energy of the protons when they emerge? 26.4 Magnetic force on a current-carrying wire. Wire segment of length L carrying current I. If the wire is in a magnetic field, there will be a force on each charge carrier resulting in a force on the wire. Flexible wire passing between pole faces of a magnet. No current in wire. Upward current. Downward current, 26.4 Magnetic force on a current-carrying wire.